Okay, so in the second section, I'm going to introduce what is the GLM, or what is the General Linear Model. And I will also show you how to use SVM package to perform the GLM analysis on the preprocessed FMI dataset. So as you processed in the last and in this week, you may find out that we actually use the unbacked dataset for the image analysis. So this is the procedure for the two-back analysis. Actually, we use the block design, and we have the alternative resting and task block during whole imaging section. And we have the 5 blocks right here. During each blocks, we will display different 6-digit numbers on the screen sequentially, one by one. We take the two-back experiment as the example, that the subject were asked to give the response once they see a number, a 6-digit number, is exactly the same with the previous 2 number right here. So in this case, 1, 3, 5, 4, 6, 5 is actually the same with the previous 2, this number right here. So in this number showing during this number showing up, the subject need to press a button to give the response that he think or she thinks that this number is matched the criteria for the two-back experiment. And again, during this kind of block design, we may anticipate they may have some brain regions will have or exhibit the FMI bold pattern that consistent with our experimental design. So in this case, we have block right here, so we may anticipate that of course, the visual cortex may have the pretty similar file because we use the visual stimuli right here. And also, for the working memory study, such as the MPEG right here, the dorsolateral prefrontal cortex is always a very important region right here. Actually, the bilateral dorsolateral prefrontal cortex right there, they may have the pretty similar pattern that consistent with the experimental design right here. So what a GLM, General Linear Model, will do is try to go through every single voxel to confirm or to estimate whether this voxel may possess the similar bold signal pattern with the experimental design. If yes, then we may have the high confidence to say this voxel or this brain region may be the region that's highly related to the two-back or working memory study right here. So we may take one of the voxel as an example. We definitely can have, I think, over 10,000 voxel signals right here. We may take one of them as an example. So we say the bold signal. Now I put this in the vertical way right here. If we say that we can measure or observe the one of the bold pattern from one of the signal right here, this is the measured profile right here. And also we have the experimental design. In this case, this is not our experiment. This is actually cropped from other slide. So they only have the block design in, I think, for example, this one, they have 4 block design right here. Okay, and this is another condition right here. So in this study, in this case, they have one condition called condition number 1 or X1 right here. And they also have a condition 2 right here, they call the X2. For example, you may ask the subject to do the left hand grasping and the right hand grasping during one FMI session. Although in our case, we only ask the subject to do one back or two back condition during one imaging acquisition period. Okay, so now you have condition 1, condition 2, and normally we will have another horizontal, although now it's put in the vertical way, but actually this is a horizontal constant profile right here. That means I can adjust the average or mean value between the experimental design and between the measured profile right here. So we will give one horizontal or constant profile right here. We call X3 right here. So in this case, we will have these 3, we call the regressor. This is just like the multivariate regression right here. So you can see we have one regressor right here, another regressor, and a third regressor right here. What we are going to do is the white profile is the non-variable right here because I designed the experiment. I designed the experiment so I know what kind of the anticipated hemodynamic should happen right here. So this is the already non-parameters right here, or non-variables right here. And this yellow one is the major signal right here. What you didn't know right now is the parameters for these regressors. What kind of a linear combination should be estimated or should be used to really make the linear combination of all three different variables become this one, or become pretty similar to this one. This is more like the multivariate regression. So beta 1, beta 2, and beta 3 is the unknown parameters that the general linear model is going to estimate. We take one of the example. If I say the beta 1 is finally to be 0.83 right here, beta 2 is become the 0.16 right here, beta 3 is 2.98. It's more like the mean value shifting between the experimental design and the major signal right here. As you can see right here, with this kind of the combination, actually you will see the combined signal right here is the white profile right here. It's actually pretty similar to the major signal right here. So that means with this kind of the parameter setup or estimation, we can say the very first one, or the x1 variable, or the first condition is actually dominant this kind of the signal, bold signal profile right here. That means this voxel or this signal may highly correlated with this kind of the condition. Or we can say this signal may reflect the brain activation or bold activation with the first condition right there. Okay. So what you can do is you will go through all this kind of the parameter estimation using the GLM on each voxel pixel right here. So every single one voxel right here, it definitely will have its own bold profile right here. Some may look in this way, look like in this way, or in this way. But you can definitely identify the three parameters based on your experimental design or based on the GLM model design. And then you can put all the numbers. For example, this one, is the beta 1 is equals to 0.83. In this pixel, the beta 1 is equals to 0.03. For this pixel or this voxel, the beta 1 is equals to 0.68. So now you can combine all the beta 1 values into so-called beta 1 map right here. That means this is a map that I can say for the region right here, this may highly correlated to the condition 1, because you can see there are high value right here, higher beta value right here. Again, you can do very similar things where I can extract all the beta 2 value from each pixel and mapping it to the corresponding location right here. Then now you can have the beta 2 map right here. And you can see, oh, beta 2 map right here, they don't have the so-called hotspot or high beta 2 value. That means none of the brain region or none of the brain voxels are correlated to the condition 2 right here. And the final one, as we mentioned, is more like the constant adjustment or the mean value adjustment right there. So you can see the distribution of the beta 3 map is more like the if you know the T2 weighted image, you will say this is pretty much like the T2 weighted image. That the ventricle area will have a higher value to adjust the mean value right there. Okay, so in this case, we may interested in one of the map. For example, the first map, I'd like to see which pixels or which voxel may have a higher beta value. I can perform the statistical analysis on this kind of beta map to say whether I have the sufficient statistical confidence to claim whether this location is the brain activation respond to the first condition right there. How you can perform this kind of GLM analysis using SPM? What you should do is to press the button again on the SPM menu right here. There is a button called Specify First Level. And you may see that there is a Specify Second Level button right under the first level button right here. You can simply remember what the difference between these two buttons right here is. First level, that means you try to perform the GLM for one single subject. It's on the single subject level. Second level, that means you are going to perform the GLM on the level of the group study. That means you have so many different subjects put together to perform the GLM. So today we will only use the single subject level. We call it first level GLM analysis right here. Okay, so you can do this. Just come to your SPM menu right here. Okay, you just click the specify first level. Again, the batch editor will pop out. Just wait a second. Okay, you can see this is the shrink the window. This is the model specification. What model? The GLM model right here. Okay. So what you need to do, we have several different parameters. I actually list all the parameters that you need to specify or key in when you try to analyze the data that we acquired for the MBAC study. So this is the parameters for the MBAC study that we used. Okay, so let me go through each of them. The very first one is a directory. The SPM will generate a file called spm.mat file within the specified folder. So normally I will specify the folder to the data folder. So now, I should switch my current folder now. Just wait a moment. I'd like to switch to my data folder, this one, and the process. Okay, this is my data folder. It will be easier. So the directory, I will select for example, if I'd like to take the 2back as the example, I will select the 2back folder as the output folder, this one. And then units for design, you can pick either scans or seconds. Believe me, scans will be much more easier. You don't always think about what is the TR, what is the interval between follows. Just use a scan, this will be more convenient. So I will select scans. And now it will ask you what is the inter-scan interval. That is the TR. That is the TR, the repetition time. What is the time interval between this file to the next file? Okay, so in our case, again, you can go back to the PowerPoint slide number 6. You will see the TR is actually equals to 2000 milliseconds. And again, the unit right here is in seconds, so you don't need to key in 2000. Just put 2 right here. And then micro time resolution, you can see the information panel right here. Actually, it will tell you that if you do use the slice timing correction, you need to key in the number of slices specified in slice timing correction step. So in our case, this should be 40. We have 40 slice number. Okay, and this one, micro time onset, this is actually the reference slice that we use for slice timing. So as I explained in the previous hour, we use the first slice as the reference slice right here. So put 1 right here. I think the most important part is the data and the design right here. Now you need to do, what you need to do is to double click. Every single time when you double click on this data and design selection right here, it will generate a new condition for you. Okay, it will generate a new session for you. Okay, so now you can see we now only have 1 subject and 1 session, so you only need this one. Okay, and now you need to select the scans. So I will double click right here. Now I will select the 2back, and again, scans, I definitely want to use the imaging with the fast field correction and normalized, and a smooth and normalized. Okay, so I will use these kind of things to be the file filter right here. You can put a head. That means you can press the Shift with 6, number of 6 on your keyboard, it will generate a hat symbol right here. And then come with the M and S. M means the bias field correction. S means smooth. That means I can use this kind of a file filter. So I don't really need to scroll over all the files. I just need to use this filter right here. Now you can see only the files start with the M and S prefix right here will be displayed on this panel. So again, right click on your mouse, select all. Again, 165 files right there. Click down, and then you need to specify the conditions. What is the condition? That is the regressor right here. As I mentioned, in this case, they have 1, 2, and 3. In SPN, you don't need to specify this one. SPN will automatically generate this one for you. So you need to specify the experimental condition by yourself. What you need to do is, again, you need to double click on condition to generate one new condition right here. In our 2-back case, I only have one condition that's called 2-back. So I only need to click for one time. If you have another condition, again, you need to click again, double click on this condition again. Then you can see I can click new condition. Now you have condition 1 and condition 2. That means you have 2 regressors, okay? But now I don't really need 2 conditions. I only have 1. So I will delete condition 2. I only need condition 1. So now the name you can key in our case, I can say I'm processing the 2-back data. So I may use the 2-back right here. Okay, this is the name. It's kind of a label. So you can key in whatever you want, okay? It's just kind of a label. So you can tell what kind of data you're processing right now. Onset, it's important to key in the right time for the onset. As you can see, the regressor is pretty important to show when the box function will coming up. It depends on when you start to let subject do the 2-back experiment, right? So the study onset depends on what kind of block design you are using. In our experiment, actually, we put the 15 scans as the duration, either for the resting period or for the unpack task period. They all set to be 15 scans interval right there. Okay, and the onset time point is actually, this is the first scan, and then after 15 scans, the 16 scans, right at the 16 scans, the subjects will start seeing the 6-digit number on the screen and perform the 2-back study right there. So this is the very first onset time, the 16 scans right there. And then next one is started at the 14.6 scans right there. So in this onset setup, you need to specify, we have 5 blocks, so you need to specify 5 values for the starting point for each task block like this. So what I'm going to do is, again, now I will double click on duration. What I can do, I don't really need to key in. I only need to know my very first onset scan is 16. And if you know how to coding in MATLAB environment, what you should do is put in these things. What does this mean? I will start from 16 with an interval 30 scans till the 165. Press OK. MATLAB will automatically calculate the onset time for you. Otherwise, you can just key in 5 numbers by yourself. Okay, it's pretty okay. If you don't know how to do the MATLAB coding, you just key in these exactly 5 numbers right here. So if you have 5 blocks, you definitely need 5. Oh, sorry, I didn't key in the right side. This one, onset. Again, 630 and 165. And this one, duration, means how long will the task will be performed. It's actually continue for 15 scans. Okay, so this is the durations. How long? Okay. Time modulation, you don't need to select. This is the things that will leave blank right there. And this one, multiple regressors. Actually, not only the experiment condition I will use as the regressor, I will also input the realignment parameters as the regressor. As I mentioned before, actually the head motion will cause larger effects compared to the hemodynamic change on the board data. So actually to eliminate all the potential head motion effects on your FMI data, I will also use the 6 column parameters that are acquired from the realignment process. That is the 3 columns for the translation, X, Y, and Z, and 3 columns for the rotation, roll, yaw, and pitch. I will select these 6 column parameter as the regressors too. So what I'm going to do is, I go to the 2-back data folder, and now you will see, as I mentioned before, you will have a file that with the prefix RMP, and then with the file extension as the text file txt. This one is actually the file that actually recorded the 6 column parameters that estimated by the realignment step. So I will use this as the regressor too. And I think you don't need to change any other things. Okay, that's all. So what you can do right now is you can just press the run batch button right here. Okay, if you already performed the model specification before, you will see the warning message right there. If you didn't, you won't see this. So now I may say, oh, continue, just continue. So it will override the previous SPM file that you generated before. Then you can see this. I think I have an enlarged one right here. This is the model design that the SPM displayed to you. The very first regressor is the block design that you just specified there. And then this 6 column, as I mentioned, the first 3 columns right here are the translation parameters that's estimated by the realignment step. You can see the translation along x-axis, y-axis, and the z-axis right here. Okay, and these 3 columns are the rotation parameters right there. Okay, roll, yaw, and pitch. I don't know the order, but just roll and pitch. Okay, so now you can see the final one is the constant. You can see the constant right here. This will be automatically added in by the SPM. Okay, so now this is the full GLM model that you are going to use to estimate the beta value for each regressor right there. Okay, and you can see there is a horizontal bar right there. If unfortunately you see some block is not white but it's actually gray, that means you didn't have a uniquely. That means this is not the independent regressor in this model. That is a bad thing because I mentioned before, SPM will assume that each regressor should be uncorrelated or independent with each other. Then you can estimate the beta value in a better way. So this is kind of the way to check whether your regressor may have the high correlation with each other. If not, you will see full white right here. If you see some column has gray value right there, that means you need to modify your regressor. Okay. After you specify your model, the next step is to press or click the button of the estimation right here. So I'm going to do this. Sorry, not this one. Come back to the menu right here. Now what you can do is click the estimate button right here. It's a relatively simple setup right here. All you need to do is to select the spm.met file. So now you need to go to the folder that you actually set up for the model construction in the previous step. Now we go to the 2-back. You will see there is an spm.met file. Just select this one, click done. Okay, that's all you need to do. Now run the batch. Just wait a moment, it will take, I think it will wait just a couple seconds. Okay, done. Once everything is done, you can again go back to the SPM menu right here. Now you can see the results. So press the results button right here. So remember the order from the specified model, then estimate the model. Finally, you can check the results. Again, go to the to-back data set, data folder, and then select the spm.mat file again. Okay, so now you will see there is a new window pop up. Let me use the PowerPoint. This is so-called contrast manager right here. Contrast manager is so important because you actually have several different regressors right here. But which one is the target you'd like to discuss, or you'd like to view the brain activation map? You need to identify this point. And sometimes you may have different conditions within one imaging session. For example, you may have a left hand grasping and a right hand grasping. You can set up a so-called contrast. That means I can use the right hand data set to minus the right hand data set to see what is the brain activation difference between these two different contrasts, these two different conditions. We call this kind of the difference as the contrast. Okay. And in this data set, you can see I'm actually only interested in the very first one. This is the block design for the two-back study. So I will actually design a contrast only with the one value right here, but others with 0 value right here. That means I don't care about others. I only want to see this one. If you want to see the contrast, for example, between right hand and the left hand grasping, you will design one contrast as 1 and another as the -1. That means 1 minus another. Okay, we will do this in the next week, not today, but you can just keep this information in mind that we will definitely use this in the next week. So what we are going to do is now you need to specify or define a new contrast. Currently, you don't have any previous defined contrast right here. So what you need to do is click the button right here called Define New Contrast. In the very first text, you can actually give a label. So again, now I say two-back contrast. And sometimes if I'm trying to discuss the difference, I may say right minus left. You can key in everything you want. It's again just a label for yourself. You can use a T contrast and F contrast. Normally, I use T contrast to statistically estimate the mean difference. Okay. And now, in this edit, you need to key in the contrast you'd like to use. What you should do is to give the value of 1 to the condition you'd really like to see. So in this case, the very first one is the one I'm interested in. So I will give 1 to the very first column. And for the rest, 6 columns, they are actually the motion parameters. I'm not care about these, so I will give 6, 0 value right here. That means I don't care about the motion regressor right here. And the final one is the constant. I definitely don't care about these two. So I will give only one value for the very first column, and followed by the 7 0 values right there. Okay, now you can press the Enter button on your keyboard. You will see there is a contrast showing up. And I can tell you that if you change something, for example, I change in this way, now I should have, for example, right here. You can see now that means you are focused on the second regressor. But I definitely don't want to see the motion right here. Okay, and there is a very convenient function within SPM, so you don't actually need to calculate how many 0 you should put. If you only give 1 right here and you didn't finish all the 0, it will automatically assume that the rest of the column should be 0. So you actually need to key in 1 and press Enter. It will work because it will automatically assume that the value or the column you didn't specify to be 0. Okay. Now, after you specify this kind of contrast, just press OK. Now it will be one of the options that you can directly select. So next time when you want to review the results, you don't really need to define the new contrast again. You only need to select this one and press Done button right here. Okay. And I'm so sorry that the word is pretty small because of the projection. But anyway, I will just just read for you. The very first option after you click done is apply masking. Normally we say none. If you have the specified region that you are interested in, for example, you only want to see the result specifically for the motor region, you can apply a spatial mask for this. But in this case, I don't have any predefined mask right here. I just press none. Okay. Then the next question, how you'd like to adjust the p-value. Because we actually performed so many GLM models, so many estimations for every single voxel within the FMI data. As I mentioned, that there are over 10,000 voxels within the FMI data. That means you already generate so many different p-value. This is so-called multiple comparison. If you only use the 0.05 as the significant level or significant threshold, that means you may insert so many potential error. We call it family-wise error on this kind of the statistical inference. So you need to correct this kind of the multiple comparison. The most restricted way we call it FWE, family-wise error correction. This is the most restricted one. You can use this one. Okay, and now you can specify the p-value. We use the default value 0.05 as the original one, and now you need to specify the cluster size. Cluster size means that only the surrounding voxel become a cluster that's connected with each other, has a voxel size larger than specified value. For example, we normally key in 30 voxels. That means only a cluster with connected 30 connected voxels. I will say this is an area to be claimed as the brain area for the activation. If there is a cluster only has a voxel, for example, 5 voxels, I will just ignore them. Okay, so this is the cluster size that you should set up. I'll use the 30 right here. And finally, there is a pop-up menu right here. You need to tell SPN, because SPN is actually used for PET imaging, FMRI imaging, and also EEG. They can use it in different modalities. So you need to specify which modality you are actually used. So now we select the FMRI. And now you can see in the figure window of the SPN, you can see the result right here. I can enlarge this from the slide. You can see now this is actually the Xray Field, not that pretty, but actually the cartoon to display where is the brain activation region when you perform the GLM followed by the FWE multiple correction with the p-value smaller than 0.05. And you can see the region with the darker labeling. That means they are the most significant area. If you see there is a white area, that means they are not significantly correlated to the experimental condition. That means this is not relevant to the two-back study. Okay, so only the region with the gray or dark or black color right there, that means they are the critical region, or the region that you can say they are the they are the region with the brain activation when the subject is performing the two-back experiment right there. Okay, and you can see there is a table right under this kind of the brain activation map. This table is actually the table of the cluster that actually pass the statistical examination. So you can actually click on the table right here. For example, each table may have a black color right here. You can click on this. You will see the label will jump to this red arrow will jump to the specific location. For example, another cluster right here, you can click on this. The arrow will jump into the location right there. So sometimes when you read the FMRI paper or literatures, you may see they always report the coordinates where the brain activations is happened, which is the specific location. That is reported right here. So you can click on this and you can see where is the location right there. Okay. Of course, this kind of the brand maps is actually, I won't say ugly, but I won't say too simple. It's pretty hard to tell which kind of the location is actually located. So in the SPN, they provide another way to display, but still not good enough. So that's why in this week, I ask you to download a toolbox called Xray View. This is a widely used viewing program for SPN. Then what kind of things you can obtain is like this one. So this one, pretty beautiful one. This is the original SPN view right here. But actually can map the brain activation map onto the subject and the topic image. Or you can generate this kind of a 3D brain mapping. Or even what we call the slice view. You can see the brain activation through different slides right here. You can use this package called Xray Field. So I hope you have already downloaded this Xray Field. What you should do is, again, you need to set a path, just like the SPN. Come back to main app platform right here. Under the home tab right here, you need to set your path. Okay, click set path. And now you need to add. You may use the add with subfolders. Okay. And now just go to the software where I put this. I think it's under there. Okay, I have the zip file. Please unzip this. Okay, now I'd like to add this folder into the main path. So now I can go to this one. This one, Xray Field, the version is 9.6 right here. Okay, select the folder. Now save and close. So what you can do right now is now you can key in Xray View, all in the lowercase, Xray View in the main command window. Xray View right here. If you set the path correctly, then you will see a new figure pop up. This is the main figure for the Xray View. Okay. What you need to do is now you can click the file button right here and then select the open images. Okay, we try to open the SPN results into the Xray View platform. Okay. So now you can go to the data folder. Now it's the 2 back right here, and I definitely know my result data will start with SPN. Okay, so now I key in this way. Sorry. Oh, why? I didn't see my result. Oh, no, this is not the right folder. My data folder is actually located right here. Okay, let me use this one. This is the right one. I didn't see SPN. Oh yeah, I do see that. Okay, this one. You can find there's a file called SPN with a uppercase T. That means this is a T contrast. If you may recall, this is a T contrast. And 001. Okay, I focus on the first condition, right? So you may imagine that if I have several different contrasts, for example, condition 1, condition 2, condition 3, you will have the so-called SPMT underline. You may have 001, 0002, 000, whatever. Just depends on how many contrasts you have. Okay. Now I just selected this single one contrast right here. Wait a moment. Now you can see this is the display right here. And in the default setup, the Xray View can actually display the positive T value as well as the negative T value on the map. But normally we only focus on the positive one. So you can select display intensity O means you will display both positive and negative, but normally we focus on positive one. So it's more like this one. Okay? And then you can adjust the P value right here anytime. If you think the p-value without the multiple comparison correction, 0.001 is too restrict. Then you can just modify to 0.05, maybe like this one. But now you will see the area become larger. Most of the region will be significant activated. It's pretty weird. So now you should actually you can use the FWE just like what we used right here. And you can see just press the enter. And you can see there is another one, FDR. If you know FDR, false discovery rate correction, you will know FWE is the most restricted one. Sometimes if you use the FWE and you see no brain activation, you can try to switch to the FDR. It's another way to do the multiple comparison correction, but in a more looser way. So you can do it in this way, so you may find some brain activation. For example, you can key in the 0.05. Again, I use the 0.05 in FWE. You can see the region is pretty small. Now I use the FDR. Now I press the button right here. You can see the region is pretty large. Again, now if I don't do any multiple comparison correction, the region becomes very, very huge. Okay, so you can pick. I think if you can use the FW, just go for it. It's kind of a standard. If you cannot find any region, then use FDR. Okay, so right now, you can click on this map any single time. For example, I want to find the dorsolateral prefrontal cortex. Sorry. Just click slowly. Maybe this one. This one may be one region. And when it comes lower, you can see there is an inferior frontal region. How I know this is inferior front region? Not only depends on your knowledge of the imaging atlas, but also you can see right here. This interface actually gives you the hint. It will based on the AAL atlas. It's pretty like the one that I provided to you. You can actually to see where is the location you are focused on. So you can try this, okay? And if you don't like this kind of the blurred image, this is actually a T1 template image. You can switch to another one. There is a list box right here. You can select a single T1. This is actually the T1 weighted image from a single subject. So you can see better the cortical folding or some structure. Depends on which kind of image you'd like to use. Okay, so you can select the different overlaid imaging that for the reference. Okay. And right here, there is a very useful button right here called Slice View. Just press on this button. It will display the activation across different regions. I think this is pretty common when every single time when you read the fMRI data, you can always see this kind of image. This is called a Slice View. And then there is a button called Up and Down. You can scroll down to see different slice cuts right there. Okay, you just focus on somewhere you'd like to see. And you can also adjust the display, the matrix. For example, I want to switch the column to maybe more, to maybe 9. Okay. Now you can see we have 9 column right here, and I can have a laser row right here, maybe 3. So now it may be better. Depends on what's your demands. Okay. You can also adjust the spacing between slides. For if you say 2 mm, that means you will get more detailed slice information right there. And again, you can switch from the transverse or actual view to the chronal view, or to the sagittal view. So this is actually a pretty useful tool for you. Okay. And the final one is the rendering view. This one we call the render view right here. You can click on this button. It will generate so many different views for the 3D image. If you want to see specific one, just click on any one you want to see. For example, this one I like to see. Click on it. It will enlarge. It will show up another figure right here. So now you can use this figure to see. Oh, there is an inferior frontal region has a significant brain activation right here. Okay. Again, the color with red means the significant brain activation. Depends on your GLM model and depends on the p-value threshold you set up. Okay, so I think Xray View is pretty useful once you finish the analysis based on the SPN, just come to the Xray Field. It will help you in very to do you a very huge favor, so you can do everything. So I think this kind of figure, you don't need to bother how can I generate this beautiful figure. Just use the Xray View. It's pretty simple. Okay. Okay. So I think it's all for today. So again, you can download all the teaching materials from my website, and please do practice all the steps. Ensure that you can really finish the pre-processing step, and you can finish the first level model specification and estimation, finally to the result display. That means you have already learned how to perform the subject-wise GLM model analysis. In the next week, I will go on the second level, and I will show you more skills about how to set up the contrast. Okay.